We have seen what happens when we measure a qubit in the standard basis. But of course you might wonder, maybe I can also measure in a different basis. Indeed, it turns out that this is possible. So let's consider our qubit. Apart from the standard basis, which we've already seen, there's another basis, which we've sneakily seen a few times, which I will draw here. And this basis is given by the state plus and the state minus. What happens now if we were to measure in this basis, given by the vectors plus and minus? Given our previous idea that we would always ask how much 0 or how much 1 is actually in the state, it is intuitive that we could now ask how much of plus or how much of minus is in our state. So to draw this here, if I ask how much of plus is in the state, how much of minus is in the state. Just as before, we basically want to compute the inner product between psi and plus to see how much plus is in psi. So the measurement outcomes, which I'll identify with the elements of the basis, so outcome plus has probability taking psi, inner product plus. And similarly, the probability of obtaining the outcome minus can be obtained by computing the inner product between psi and minus. The idea is exactly the same. We've just plugged here other basis vectors than the standard basis. Let me now summarize the general rule for measuring qubits in a basis. If the basis we are measuring in is given by the basis vectors labeled B, where B is some basis element. Remember that for n qubits, the dimension would be 2 to the n. Then the probabilities of measurement outcomes, the probability of outcome B, is given by the inner product between the state that we want to measure and the basis element B. So if I want to measure the state psi, then the probability of getting outcome B is given by the inner product between psi and B. And again, you might ask, what happens after the measurement? If outcome B occurs, then the state collapsed to B. We will also call the state after the measurement the post-measurement state. This is the rule for measuring qubits in the basis. Let's consider one example to get some practice. Let's consider measuring just a single qubit, psi, which is a superposition between 0 and 1. And in our example, the 1 will have an amplitude of square root 2 over 3, and the 0 we will have an amplitude of 1 over square root 3. Let's apply the rule to compute the probability that when I measure in the standard basis, I get outcome 0. So let me take the psi, and here I will measure in the standard basis actually, which is again just the basis, but I will choose it here for convenience. And I apply the rule of computing psi with the basis element. So in our example, we can compute this quite simply. It's 1 over third with 0, 2/3 times 1 with the 0 state. So let me do this. So we have 1/3, 0, 0, plus 2/3, 1, 0. So remember again that the elements of the standard basis are orthogonal. So this here is 0, and because all vectors have length 1, this is 1. So we see that the probability is just 1/3. And indeed, we would have expected this if we observed that this here is alpha and this here is beta. And now actually thinking back to the standard basis, because it is a special case of measuring in the basis, where this probability was always simply given by alpha squared. The probability of getting 1 we can of course also compute, and is the inner product between psi and the vector of that basis, here just 1. So you should do this computation, but of course what we expect that this is 2/3, so the probabilities add up to 1. So now you've become an expert on measuring qubits in the basis.